Good evening, everyone. I am Sandeep Anand. I am a faculty member in the department, and I work in the area of power electronics and power systems. So I belong to the E3 power electronics and power systems specialization. So what I try to do is I try to give you a high-level overview about power, and after that we have planned for like 5 to 7 minutes, very brief presentations by different colleagues from E3. So we'll try to give you a flavor of, so E3 or PPS essentially comprises of, it's like a lotus, right? You have different, it's like a bouquet, you have different flowers of different colors, but at the same time they all come together and look nice, right? So something similar. So we'll try to give you a picture of different aspects. And we have only planned it for like 40-45 minutes. So we are assuming that if we stick to that and accounting for this 5 minute delay, we'll have time for more interactions, 10-15 minutes of question answer discussion and so on. Okay, and we can take some questions in between, but I think we'll restrict to only one question per presentation, if at all anything in between, and if at all any more questions, we will take it in the end. So with that, what is power, or rather power electronics and power system? At this stage, if you see, right, unlike maybe 20 years back, things have changed drastically. Majority of the things that we see around are driven by power, right? Either power electronics and power systems. And power electronics power system, forms the basis of any of those things. So you cannot imagine those things existing without this. What do I mean by that? Let me start giving some examples. So computers, right? Mobile phones. Sizes have been coming down, right? People are shrinking laptops, mobile phones, and so on. What remains one of the biggest challenge in shrinking these is how do you power them, right? How do you use the battery energy most efficiently? How do you convert it to different voltages so that multiple chips on the mobile phone, which some of us are using right now, gets powered? How do you generate power, right? There's been, if you're reading newspaper, then there's been a lot of discussion around one sun, one world, one grid policy, right? Or rather, the proposed framework, which our Prime Minister have announced some time back, which essentially talks about connecting multiple countries and generating majority of the power using renewables, including solar. Again, if you see, right, 20 years back, people were not very keen on solar. So it all happened in last 2 decades, I would say. A lot of things have drastically changed. And things have changed for good. And power has become more and more relevant. And not just that, moving into future, right? I mean, my understanding is that, in fact, there is a book which says All Electric America, which actually talks about that everything is electric. And even if it is not at this point in next decade, everything is going to be electric. And the big question is how do you power that electric, right? At the load point, at the source point, and so on. Let me go back a little bit, I think 10-15 years back, where, I mean, that time Google used to be probably the most quote unquote favorite company, right, of everybody, irrespective whether you want to work in software or not. So Google floated something called as a little box challenge. Now, what was this little box challenge? This was essentially developing a inverter which should be the most compact inverter in the world. So that was the challenge, and that was the first time, at least I got very excited because I thought I mean, Google is trying to get into power, right? It looks that way. So I was very excited about that. Obviously, eventually, now, I mean, you guys don't have to use the same example because you have companies like Tesla who has come up and they have, just sort of completely revolutionary kind of an approach which they have taken, and that sort of substantiates the more and more need of power moving forward. I'll give you one more example. So I don't know how many of you know, but there was a company called Eddy Electric, right? So eddy currents, right? So there is this the way we feel all fancy about Tesla naming the company by a scientist Tesla. So eddy current, if you see again, it's a very sort of technical name, kind of nerdy name, and this company started in India back in 1993, and they made EV electric vehicles, and they called their cars lovebirds. but it didn't fly off, right? Because they were trying to do something which was at a different time, at a different place, which was not favorable. Now, with that, let me tell you, now is the time and the place where one should actually get into power. Probably the time when I or most of my colleagues would have got into power, yes, there were a lot of opportunities. But now it is, just the, I would say, the main thing to focus upon. Everybody is worrying about climate changes. Everybody is worrying about how we power our future, right? So this is one of the important things. Now, with that high level thing, let me come to our specialization, very specifically PEPS, as we call it. We have about 11 faculty members who are like very closely forms the PEPS group. Broadly, nowadays the boundary, has some much more, so there's a lot of overlap between the two. If you see some of the get more understanding of what all different faculty members are doing, and that's just a sample. There are quite a few other colleagues who are also doing a lot of other interesting things. In terms of students, PhD students, project staff, we are about 100, right? And the things now that we work on obviously have developed on those basic topics such as machines, power electronics, power systems. But now they have become so much multidisciplinary. I'll give you an example. For example, we were some of the students were participating for this International Future Energy Challenge, wherein again the target was to develop the smallest converter. So I'll give you more examples from power electronics because this is what I'm more focused on. But there are equally interesting examples which exist in the other or the allied areas also, and I think some of my colleagues would probably share those with you. So this was about developing a small size, small form factor DC to DC converter for space applications, right? For satellite application, you have solar panels, and then you draw power from those solar panels, you charge battery, and then you have one loads, which are essentially electronic loads, microprocessors, op-amps, and so on, and you want to power those. So how to design this power converter so that it should be the most compact and should be the most lightweight converter. The team that I'm referring to eventually won the third position globally. I think first was probably China, second was Europe, and third was our team. So why I wanted to share is because while doing that, right, students were working on how to use different types of devices, right? So a lot of students had quite a lot of overlap understanding microelectronics, right? How to design measurement circuits, again, a lot of overlap with analog circuits. How to design the control of that, right? So just now my colleague was talking about astronauts. So yeah, I think this is more of an astronaut approach and less in the way he defined it. So then in controls, how do you actually control that converter so that when it is there in space, it has practical loads, it behaves the way you want it to behave. How do you handle the heat in space, right? How do you do the thermal analysis of it? So a lot of these different things exist, and PEPS assets is a conventional field, but in last I would say 2 decades, things have changed drastically, and it has become quite a lot multidisciplinary. In general, our E3 has a very open culture. We encourage students to interact with each other, interact with faculty members, and so on. So that they don't only get more understanding about their topic, but they develop a much better width, and they can be ready for, let's say, changing technology in the future. That is it. I think that was the time 4:45 where I should stop and maybe hand over the mic to some of my colleagues. Okay, request Professor Agarwal to please go ahead with his part.
Yeah, so thanks, Sandeep. Thanks for this opportunity to speak to our youngsters, the DD students of the third year. The time allotted to me is about 7 minutes, so it's really too short because PEPS is a very wide and very vast field. To tell you the activities we are doing here, it's a very big group of faculty members and students, so a lot of activities. So what I'll do is I'll just share my screen. I have just put together some pictures for you. I don't think I can really talk too technical here. I'll just try to just show you some pictures and maybe give you some ideas about what activities we are doing here. So I'll just go to the slideshow mode. I hope my screen is visible and I'm audible. Okay, so
Yes,
I
I
assume
can.
that,
Yes.
yeah, thank you so much. So let's start with a glimpse of activities that we have here. We work in several areas, the non-conventional energy or the renewable energy, where we talk about the modeling and the dynamic characteristics of the solar photovoltaic rays. We work with fuel cells and we work with wind energy sources as well. We work for the various types of power converter topologies, for both standalone and the grid connected systems, as well as for the fuel cell and the wind systems. We work quite a bit on maximum power point tracking of all these renewable energy sources because they have a very peculiar characteristics, IV characteristics, and we need a lot of efforts to actually draw the maximum power from there. We also work on microgrids. Power electronics is an area where we take a lot of help from electronics. So many of us in the power electronics and power systems PPS groups are also working for the electronic systems group. And these are some of the activities, though they may be little off the track here for this presentation. We have been involved with that as well. Power conversion and electric drives, we have a again, a lot of activities in this in the PPS group. New power converter topologies, which are more efficient, which are more compact, and which make use of things like high frequency link for compactness and low weight and so on. ZVS and ZCS configurations. I'm sorry, I have to use these terms, but they're very important. They are for again reducing the switching losses as the switches in the power electronic converters they switch. So actually to reduce their losses, we use these schemes. We use several advanced control schemes for our studies. We have some very special types of power converters, a switched capacitor, DC to DC power converters, which are extremely low weight and they don't have any magnetic components. So they are very compact. And we also work on sensorless controls of electric drives. We also work on power quality issues. Our power systems today is not a very clean, a source of energy. It has got a lot of spilled, dirty waveforms generated from the nonlinear characteristics of loads which are connected. And therefore, we need to clean up these power systems by using certain power quality measures. And we use power electronics for that. And we also work to some extent in what is called electromagnetic interference and electromagnetic compatibility. EMI, EMC issues we are very active in electronic systems and power electronic systems as far as the EMI, EMC research is concerned. I'll be glad to answer any questions that you might have immediately. Then, these are the current areas in which we are currently focusing. One of the areas in which we are focusing in a very big way is the EV charging. So today you must be hearing quite a lot in the newspapers and in the news channels about the electric vehicles. So as you know, they are all run by batteries and they have to be charged. So there are several types of charging schemes which have come up. Some of them are the wired schemes where the charges are actually put into the batteries through actually physical wires. The other is what's called wireless charging because it has got its own advantages. So it's a very upcoming, very new field, but lots of people are working on it. We work on dual active bridge, which also finds a very big application in electric vehicle charging. This is a very dual active bridge is basically a bidirectional converter, power electronics converter, and it can actually do a lot of things like it can be used for solid state transformers to make really very big transformers very compact. And big companies like ABB and GE are doing a lot of work on this. And at the academic level, people in our labs, we are also trying to work on this. We have lots of variations of power electronic systems where we are working with grid connected systems. We have the AC and the DC microgrids, various aspects of that we are trying to work. We are working on energy storage, where we are working a lot on the modeling and the interfacing of supercapacitors. These supercapacitors are actually special forms of capacitors which can actually hold a lot of charge, unlike the ordinary capacitors that you are familiar with. So they have actually porous electrodes, and the charges can go and hide themselves there, giving a lot of capacity to such capacitors. We are also doing a lot of work on elevators and home appliance motor drives. In elevators, currently we are trying to work on gearless PMSN drives. And last but not the least, we are quite active in the multi-level converters, where we are looking at the multi-module converters, the MMCs, which have again a very vast variation for high power. So just in case you're curious, a power electronics engineer today is a person who has an extensive power electronics hardware knowledge. He's known for his knowledge in electronics hardware. He has to learn a lot of simulation softwares like MATLAB, Plex, PSIM, LTSpice, etc. He also is aware of embedded programming. He uses VHDL, C language quite a bit, and a very extensive use of digital signal processors. Okay, all these modern processors, which actually have some special features which are suited for power electronics applications, are now available. People are also using these field programmable gate arrays, FPGAs, and so on. And of course, the development of all sorts of control algorithms. So a power electronics engineer today is actually having lots of these skills and backgrounds. These are some of the activities where you can see some solar PV modules mounted. On the right side, you see a flexible PV module, which are actually a thin film technology, and these are being extensively used in places where you want to use the PVs as skin. For example, building integrated PVs and so on. These are some of the characteristics of PVs under very special conditions, and actually they really give a lot of challenge to actually track the maximum power point from a source which is having these kinds of characteristics. So this actually opens a very big scope of work. A lot of work is being done still. 2-3 decades have passed, but still I would say a lot of scope is there to work in this field. These are some of the pictures that where we have made. We've used fuel cells. A fuel cell is a battery which is continuously charged. So you have the hydrogen and oxygen as sources, and what we have is a polymer exchange membrane type fuel cell module that you see here. Okay, it's about 1.5 kilowatt system, and we actually made one inverter, power electronic inverter fed by this fuel cell. One of the things that you have to understand is that all these renewable sources, they have a form of electricity which is rarely compatible with the electrical loads that we use in our normal lives. So we use a lot of power electronics. We need a lot of power electronics to actually condition this power that we get from renewable energy sources like the wind or from the fuel cells or from the solar photovoltaics, to convert them into a form which can be directly used by our electrical loads. So these are some other pictures which show the wind turbine emulation, and here we show electric vehicle drive. Another case where we were trying to basically electrify one auto rickshaw. Some more activities showing the fault diagnosis of the induction machines. Again, a very, very important area. In large plants where there are several machines, it's very important to maintain their reliability and to perform regular maintenance. To make that time, to actually conserve time there, and also to improve overall performance. These are very important activities that we do a diagnosis of the machines and predict whether we need to replace the machines or maintain some machines in time. Then these are some of the things that we have done in collaboration. It's a smart power module for power quality applications, which we actually developed in collaboration with Microsemi. It was called Advanced Power Technology Corporation in the US. With their help, we have actually developed these power modules, and they find a lot of applications in UPS and power factor correction schemes. This is one of the latest facilities that we have got in one of the labs. It is the grid emulator. We work a lot with converters which have to interact with grids, and we must be able to simulate, therefore emulate several conditions on the grid and basically test the converters with them. So what you see here on the left side is a very high power converter. It's a multi-modular, as you can see, modular multi-level converter, and we are trying to test it with the grid emulator. And this is probably the last slide. Yes.
Yeah, sorry, this is Sandeep. Yeah, so yeah, I just wanted to hint that we are exceeding the time. So please,
No,
yeah,
no,
go
no.
ahead.
I just thought this is my last slide.
Yeah.
So this is just a setup where we made a power pack using the ultra capacitors or the super capacitors, and these are being tested using this heliostat. It actually is an impedance analyzer which can actually convert to the properties of the super capacitor. So that's all. I just conclude my talk, and I am available now or after the all the presentations are over to answer your questions. Thank you very much. Thank you so much. I'm
Yeah,
stopping to share my slides
thank
now,
you.
my screen. Yeah.
Yeah, thank you. I think I request Professor Anupama Kohli to maybe please share the screen. And meanwhile, if anybody,
Are you guys able to
Anup,
hear me?
yes,
Okay. Let me just share my screen. Are you able to see my screen?
yes,
All right. Okay. So I'll not take
but
too long.
not in the full screen mode. Not in the full screen mode.
Okay. Give me just
Yeah.
1 minute. Sorry. Thank you, Sandeep. Is this better? Are
Yes.
you able to see its full screen now, everyone?
Yeah.
Okay. So I'll just go over a few of the slides I have here, not all the slides. Just a couple of things I want to point out. Do you guys know that electrification was ranked by National Academy of Engineering and in several other surveys as one of the greatest achievements of the 20th century, which means electrification tops aeroplanes, electrification tops computers, electrification tops internet, which, believe it or not, you might find it extremely scandalous. How could electricity top internet? But that's what it is. And you would think that for how long electric systems have been around and for how long machines and power systems have been around, we would have all challenges figured out. But here we are, come 21st century, still trying to figure out what do we really do to make electricity systems function better, make devices function better, make devices consume better. And that's because electric sector is one of the biggest consumers of energy, and it's also one of the biggest suppliers of end use energy. But what I mean by that is it's one of the most used energy delivery infrastructures. Okay, and for that reason, it's also one of the biggest consumers of primary energy sources like coal and so on, which also makes it one of the most visible sources of greenhouse gas emissions like carbon dioxide and so on, right? So when it comes time to figuring out how to decarbonize the system, where to apply carbon sequestration, one of the first things someone is going to think about is electricity. And you may know that India also has taken very, very aggressive steps in terms of making sure our demand is met in the most sustainable manner possible. So we are very much trying to focus on use of solar, wind, tidal resources to try and meet our energy needs. But there are some challenges. So what I have here is, for example, data from a residential community, and if you look across the year, it seems like it's really net zero. They produce as much solar production as they consume energy, but then it's not really coincident, which means the grid has to bear the grid is effectively acting as a big battery for this solar for this community, and that has its own challenges. So what my group tries to do is tries to figure out how do you actually make sure that the renewable supply we have can match the demand we have in the most economical manner, in the most reliable manner, and in the most sustainable manner. Okay. And one of the things that I want to talk about today is this approach we have developed here to manage energy in end-use buildings. So what we try to do is, at least from an economic and efficiency point of view, try to make sure that buildings consume energy much, much better. And in most urban buildings, residential buildings, there are a few key sources of heating and cooling, which are the biggest guzzlers of energy. So your water heaters that you use in the morning for your shower, and your air conditioners, those are your biggest sources of energy consumption. So we have worked out algorithms here that can use the Internet of Things approach, it can use the big data approach to really make sure that these systems consume energy only when they really need to consume, which means you use your electricity and air conditioner and lights only when there is a person in the building, only when, you know, and I try to optimize it to make sure that you're not overcooling the system or you're not undercooling the system. And these have its own challenges. We have been doing a lot of field trials here. You may have seen some of our test beds. Those of you who were here for a very short period, if you had visited the conference room, we have been using a lot of sensors to map out the thermal distribution in space and try to figure out how to influence this thermal distribution in the most energy efficient manner. And this has a connect to grid as well, right? Because you would ask, what is you as a power engineer doing? Why are you doing all these things? And that's because, believe it or not, these air conditioners consume a large fraction of the electricity demand during peak hours, which means when the grid is in stress. 2016 figures put this at 10% of the peak. And they are also one of the most widely used resources in US and Europe to bring down the electricity demand when things get too hot. So typically in July and August, you might see news reports where, you know, so many thermostats were turned off or so many air conditioners were turned off to save energy. And if you guys have heard about the Texas blackout, that was also heating, electric heating, which had brought down the grid at that time. And there were a lot of other resources also responsible for it. But that sort of brings to focus why these systems are important. And this is what my group primarily does. We also work on a lot of things like analytics in general for managing supply and demand. So we've developed a few analytics for electric vehicles, like how would, if a car park operator had to ensure which electric vehicles to charge based on a deadline given to him, how should he do it so that he can either adhere to the limit, consumption limit from the grid, or try to maximize solar power as much as possible. So all these sort of control and optimization algorithms based on real world statistics as much as possible, we try to work on here. And that's all I have to say.
Yeah, thanks. Thanks, Anupama, for sticking with the time. So I think maybe we'll continue, and if there are questions, we'll take later then.
All right, no problem. I'll stop sharing.
Yeah, thanks. So I think next is Professor S.V. Kulkarni.
So are you able to see my presentation?
Yes, but it's not in full screen.
Okay. Now is it okay?
Yes.
Okay. So good afternoon, students and my faculty colleagues. So I am going to share what my group is doing on. So basically, I work on these three areas: electromagnetics, insulation diagnostics, and transformers. So first, I would like to show you the high voltage setup that our department has. So this is on second floor. If you happen to visit, there is something called as insulation diagnostics lab with a big Faraday cage, and you have inside it 100 kV AC and 140 kV DC setup for doing research on insulation engineering and diagnostics. So other facilities we have are basically Epstein tester for magnetic circuit characterization, electrometer for measuring very low currents up to picoamperes in insulation, then tabletop high voltage unit, spectrum analyzers, and some other measurement setups. So basically, my research areas are electromagnetic and coupled field computations, modeling and analysis of hysteresis characteristics of soft magnetic materials, wire electric discharge machining for slicing semiconductor ingots, transformer health index tracker, investigations on insulation degradation in photovoltaic modules, and modeling and synthesis of high energy storage devices. So of course, I will not go into details of each, but if you have some students have some questions, I will, but I'm not going to show all the slides and describe everything. So first is you students must have undergone a course on electrical machines, and even in your first course on electricity and magnetism, you might have studied hysteresis. So when it comes to hysteresis losses in transformers and rotating machines, you need to have a deeper understanding of the hysteresis phenomena and how do we model that for accurate calculation of magnetic circuit losses. So there are many complications in hysteresis loops because of anisotropic nature of magnetic materials. For example, in rolling direction and transverse direction, you can see the hysteresis loops are quite different. Because of harmonics, you have minor loops, and all these need to be properly accounted for if you need to calculate hysteresis losses accurately. You can also see with increase in frequency, the hysteresis loop bulges, and those complications are there. So when magnetic devices are subjected to power electronic supply systems, then you have, because of harmonics, you have multiple minor loops, and then you need to have proper analysis and modeling of such loops. Also, our rotating machines and transformers and other magnetic devices, they need to be clamped, and due to clamps, the magnetic circuit gets mechanically stressed, and then these hysteresis loop get modified due to the mechanical stress. And we are doing some work on identifying how the stresses affect the magnetic circuit losses. Similarly, the temperature also has an effect on hysteresis loop, and this effect is significant for materials having low Curie temperatures. For conventional grain-oriented materials which are used for transformers and rotating machines, that problem is not there because the Curie temperature is something like 800 degrees centigrade. But otherwise, the newer materials that are being used in particularly power electronic applications like ferrites, amorphous materials, and nanocrystalline materials, you need to worry about temperature effects also. And then there is one more special topic called as rotational magnetization, which happens in transformers and rotating machines, motors particularly, because of the superimposition of three-phase fluxes. You have the flux rotating in some specific parts of the machine, and rotational hysteresis losses are much higher as compared to conventional hysteresis losses, and we are trying to investigate these losses by using some experimental setup. We are also we have already developed one cost-effective characterization tool for measuring hysteresis. Of course, it is not yet in a packaged form. It is not packaged in a box and all that, but we can right now measure losses up to 500 hertz by using this, whereas the commercial hysteresis measurement setups are quite costly. So the next topic I want to share is duality circuits and complex permeability based modeling. So basically, many electromagnetic devices can be analyzed by complicated, finite element analysis and all that. I don't want to get into details of that, but that is quite computation intensive, and there is a trend to go for simplified circuit analysis by using duality between magnetic and electric circuits. So you convert a given magnetic circuit into its equivalent magnetic circuit by using MMF and reluctances, and then convert it into equivalent electric circuit, right, by using duality principle, and then things can be computationally simple. So this is one area that one of my students is working. And then here you can actually model the hysteresis loop that we have seen in the first part of presentation by using what is known as elliptic loop. So this original hysteresis loop is modeled as an elliptic loop, and that can be, effectively you are linearizing the magnetic circuit for representation, and that simplifies computations. So if you are interested in calculation of losses, then this approach is much better. Then the third topic is on insulation degradation in photovoltaic modules. So as you know, solar PV modules are being installed in India on a large scale, and probably some of the reliability aspects would be important to study in coming years. So one such aspect is insulation degradation in such photovoltaic modules. And because if the insulation degrades, then whole that module needs to be replaced, and a lot of downtime would be there, and loss of available electricity. So one of my PhD students, she is working on what kind of degradations can occur and how do we characterize those degradations. So basically, how do we, typically solar PV module is shown here. PV cell is shown in this dark gray, and these are the corresponding insulating materials surrounding that PV cell, and then this is the PV module, and then this is the frame structure. So obviously there is a voltage difference between this frame, which is at ground potential, and this cell structure. And if that insulation structure degrades, then over a period of time, it could lead to reliability issues. And then there is a, how do we model this? There is something called as Arrhenius equation, which tracks insulation condition. So we are trying to do some experimental measurements and, validate our theoretical analysis. Next is modeling and synthesis of high energy storage devices for devices. So here, you know that because of various renewable energy applications, and also, emergence of electric vehicles, the energy storage is becoming even more important these days. And, one has to basically understand how do we pack more energy in a given dielectric material. So a lot of research is happening in this area. One of my PhD students, he is working on understanding what are the factors that influence energy storage, and how we can enhance energy storage capacity of a given dielectric. Right, so there are two basically parts of permittivity: real permittivity and complex permittivity. Real permittivity is the one which basically indicates high energy storage capacity, whereas imaginary component is indicating lossy nature. Right, so idea is to basically increase the real permittivity and reduce the complex permittivity. So the student is, trying to build a theoretical model of a typical bilayer, dielectric structure, and trying to understand what are the different polarization mechanisms which influence energy storage capacity, and how do we suitably modify the material or interfaces to increase the energy storage capability. And then he will eventually also be using quantum mechanical model for bilayered multilayered dielectrics, and trying to understand how energy storage can be, improved by analyzing various factors like damping, and he will go into more of physics also to understand various mechanisms that are happening.
So, Professor Kulkarni, sorry to interrupt, but I think we are overshooting the time. So
yeah, okay. So then I stop it here. So one last statement. One of my students is also working on EV electromagnetics, the electromagnetic aspects of typical electric vehicles. Thank you.
Yeah, thank you. So I think next is Professor Anil Kulkarni.
Yeah, I hope you can see this.
Yes.
Yeah. Okay. So yeah, I'll keep myself very short. Uh, our group, which includes many of my colleagues, who have already spoken, and also Professor Soman, who is not here, focuses on power system analytics, very specifically development of analytical tools, or in short, programs which help in the modeling and analysis of power systems. And as I shall emphasize here, most of our work here is oriented towards the industry in power systems, and also looking at newer applications which are born out of our own experiences. So just go to the next slide. One of the recent activities which we have been working on is the use of phasor measurement units, that is units of measurement which are GPS synchronized, which are spread all throughout the Indian grid, that is quite literally from Kashmir to Kanyakumari. And we get all this data, and this large amount of data is essentially streamed every 20 milliseconds to energy control centers in India. And we are in fact working with organizations like Power Grid Corporation of India and JETCO to develop analytics based on this. And just to give you an idea, and there's too little time to talk about the complete details of this, it involves use of this data, which is essentially like like a snapshot of the system at a given point of time, and developing analytical tools around it in fact involves a fair degree of programming and analytical skills, so that you can use this data not only for online monitoring, but also possibly for real-time control. And in fact, some of the tools which we have developed so far have been now deployed in many of the control centers in India. So you'll find that these are essentially C and C++ programs which have been developed for several applications. And just to put these things out in the sense that you hear them, and you'll take a bit of time, and if you join our program, you will of course learn more about it. But essentially, they are in terms of improving the behavior of protective relays in the system, grid control, improving the stability of a system, preventing blackouts effectively, like doing adaptive islanding, and of course more mundane activities like estimation of the states and calibration of instrument transformers. And all these activities are in fact being carried out with students like in our laboratories in IIT. My colleague Soman also is involved in the problem of load forecasting, and also in fact forecasting for wind and renewable energy. And here too we have developed tools essentially which are using advanced mathematical techniques for this application. And again, a major focus of our work, since we are engineers, is to see that our applications actually reach the industry. So in fact, some of the tools which we have developed have been deployed in organizations like Tata Power Distribution, BEST, and TANGEDCO. In fact, some of the tools like wide area measurements, etc., are now practically like products which we would like to license out to people who would like to use them or take them forward. Incidentally, my colleague Soman also works in developing tools for electricity markets. As you may have heard, that India has several power exchanges in which people can trade in electricity, and we need to have, of course, optimization tools to, in fact, try to, in some ways, determine spot prices and the schedules, corresponding schedules. And we find that many of the theoretical concepts, in fact, are useful one more area where we have been working on is on policy and regulatory issues and cost allocation, and also again developing tools for the same. And some of the tools which we have developed are in fact deployed in Power Exchange and the Regulatory Commission and the operating power system operating company. So on a more nuts and bolts point, we also are looking into a development of relay hardware and algorithm designs. These are essentially devices which protect the system, and you need to develop appropriate logic so that only the device, whenever there's a fault in the system, only the devices which are or equipment which are faulted have to be removed from the system. So these essentially relays have sophisticated algorithms which need to be designed to differentiate and determine where faults have occurred. So we are also using this kind of we are working on these kind of aspects. In addition, of course, we work on modeling and simulation and any other analytical aspect relating to power systems. Incidentally, the impact of communication and internet technologies have had a very big impact on how power system analytics are being developed today. And we hope that some of you would be interested and join our group to work in these areas. Thank you.
Thank you to all the colleagues who have
Thank you.
came and presented to students, and thanks Priya for hosting it, and any other students who have put efforts in hosting this thing. And yeah, thank you for attending.
Okay, thanks, Sandeep.
Yeah. Okay. Thanks. Yeah. Bye.